All right, good morning. Another Physics Teachers Are Awesome video reaction. So today we're doing parallel mirror ray diagrams. Based on the title of this YouTube channel, I think this might be high school level, but I'm not sure. So here we go. Oops, let me turn it up first. There we go.
Alright, good afternoon everyone. Today I'm going to be showing you how to draw ray diagrams for a parallel mirror problem.
Cool.
Now, these parallel mirror problems are going to show up a lot throughout this unit of physics. The big thing about them is we have two mirrors that are side by side with some form of object that's being reflected.
Cool.
I think I promised you gold stars on your test, so I can give you gold stars to place places. Now, here we have this nice little black and white domino. It's really handy because it allows us to see the different ways that we might be looking at an object.
Oh, I like that.
Reflected across, and we can easily see if the image changes direction.
Boy, I really like that. You know, when we do these little arrows, which are common in ray diagrams, there's not really a difference between their front and their back. So I really like this very, very simple black and white. It's got a little bit of dimensions and directions in both left and right and up and down. And the left-right, the black-white is going to help. I wonder whether the students would ask, well, why not differentiate top versus bottom? Turns out in this entire setup, top versus bottom is never going to change. Every single image that he ends up drawing is going to have the same top and bottom. But it's interesting. I wonder if that would be a really cool, additional question to ask of the students.
The other thing we have is an eyeball down here. This represents you looking into this parallel mirror setup. We have mirrors 1 and mirror 2.
Cool.
Now, the first thing I do with any of these is I reflect my mirrors in each other. Now, one handy trick that I have found for the layout in the packet is that essentially the spacing between the two, and we want to be careful to measure. In this case, I see the spacing at about 25, 26, a little over 27 millimeters. I'm going to approximate that as the width of one ruler.
Nice.
I'll put my ruler between them, and I'm going to create my mirror reflections using my ruler on either side.
Nice.
Because my ruler is essentially the spacing between those two lines. And yes, that was on purpose. We wanted to give you a simple way to copy down a mirror diagram so that most of our classroom rulers are about.
So a little bit of commentary about the setup. This is actually a really good focal length camera. Notice that it's not doing the autofocus on his thumb right now. We can still read the page really cool. You've heard me comment about that before. So really, really great setup. We can see everything well. He's cognizant of his hand being in the way every once in a while and gets out and makes sure that we can see what he has been writing. So very cool.
About the width of that distance between the two lines. So mirror 1 gets reflected in mirror 2, creating an image of mirror 1. Mirror 2 gets reflected in mirror 1, creating an image of mirror 2.
Cool.
Mirror 1 gets reflected in the image of mirror 2, and yes, we are going to have to go out to a number of these. Mirror 1 gets reflected in the image of mirror 2, giving us mirror 1, but it's no longer reflected in an original object, it's now reflected in a reflection.
Cool.
So that's going to be a secondary reflection of mirror 1.
So I'm just quickly trying to think here if there's multiple ways I could say that there would be a mirror right here. So he's saying that this one is the image of this, but it's also... Can we also say it is the image of this in itself? I think we're allowed to say that. I mean, it's so interesting when you have these multiple reflection problems, right? There's just so many ways to do it. Some students really don't like these sort of, it's not really there, I'm not going to use it like it's a mirror. I want to bounce all of my rays and just keep all my angles identically equal. And you can do it, but it just gets, all of the clutter ends up in here, and you get these focused rays that you just then would extend and say, aha. If I dotted line extend them, it looks like they're coming from here. But what this structure helps us understand is you just think of them, they're just another mirror. They act just like mirrors. Their rules are just like mirrors. And pretend that nothing exists in between. So we'll just have rays go from this, ding, ding, like that. And so I think that it's a really great construction. I love it.
Over here, you're going to see we've got a reflection of mirror 2 in mirror 1, so we're going to get a secondary reflection of mirror 2. Alright, our mirrors are drawn.
Oh, the other thing I should comment is that this domino is not evenly spaced between the two mirrors. That's going to come in really handy.
Next up, we have our object here. And one thing I remember from before is our object's roughly... Ooh, we changed the dimensions on that object between the two columns.
He was hoping it was a centimeter.
Originally, our object was about 10 millimeters. But now we're looking at an object that is a little bit more along the lines of...
So my guess, based on how he said that this was purposely built, is the problem with perfectly spaced things on the computer, and then you print it. This happens to me all the time. I say, yep, but I measure it on the computer screen, and then I go print, and for some reason, the printer has zoomed it just a tiny little bit. So maybe that's what happened here.
Between 12 and 13 millimeters. I'm going to call it 12 for the sake of simplicity. So what we're going to do is we're going to measure the distance from that object to the mirrors. We're going to transfer that distance to the other side.
So it's interesting. If you think about what's happening here, where is his head, right? Because is he looking at the image on the computer as he does this? Like, looking away while moving his hands? Or is his head, like, right next to the camera? It's interesting. I don't know if I can tell.
Taking care to draw our images at about the same height. You'll note that I am trying to take some care to be moderately close to my original dimensions, because that's going to matter when we draw our eventual ray diagrams.
Oh, very cool.
I'm again just copying a drawing of that to the exact distance on the other side of the mirror to create my primary image. The side of the object that faces the mirror in the image. So the black side faces the mirror, and the image, my black side, faces the mirror. Over here, you'll notice that I'm looking at about a little over 12 millimeters, 12 and a half. And then I'm going to start my object right there. Again, trying to be pretty close on the height of my images so that things relatively match up. Here the white side faces the mirror, so the white side's going to face the mirror when it comes over here.
Cool.
This is also a primary image of our object. And you keep continuing that, and I am going to draw my remaining images.
So I really like this structure. I really like what he's up to. He hasn't drawn any rays yet. I'm just going to sort of fast forward until we get to some rays here. So there's image 2. He comes way over there and he makes that one. And then, let's see, go a little bit further. So he's only doing the one side. Let's listen.
Of a reflection of the object. And our tertiary, which is a reflection of a reflection of a reflection of the object. Now, we were told we need to draw to the tertiary image on the left side. So we have a little more drawing ahead of us. We have to
just
draw
gonna fast forward again.
out
I just want to see if he gets to any ray
tertiary
diagrams.
your side. All right,
cool.
So your first steps were copy your mirrors down and make your mirror images of each mirror an equal distance behind the other mirror. our next step was to repeat this process and copy down images of our original object. Now, a common question is, how did I know to stop when I only had 2 mirrors on the table? Well, you need 1 fewer mirror image than you do reflection. So, for instance, if I'm looking at the 3rd image on the left side, I need at least 2 mirrors.
Oh, that's cool.
I'm also going to need all of the images on either side because we're going to follow the same process we would for a 90-degree mirror. That process is that we will start with the image we're looking at. We're looking at the tertiary image on the left side.
Cool.
And we're going to draw our line of sight. With something like this, I just like to draw to the corner. We'll line our ruler up so that the eye and the corner of that object are all in alignment.
Oh,
we'll
cool.
Come down here,
And he's only drawing
solid
it there
line
and then
to
dashed.
the
Oh,
first
very cool.
mirror, and then we're going to do a dashed line after the first mirror. This again represents the line of sight, which is the line our brain thinks that light took when it was traveling.
Love it.
Our brain looks into a mirror and it says, oh, hey, look, there's stuff back there. But there's not. Now, the next thing we do is we apply the law of reflection. The law of reflection states that we will reflect off of a surface at the same angle we struck it at.
How's he going to do that?
So if this is the angle we hit the surface at, that's the same angle on the other side it'll bounce off at. Excuse me. Now, we can use a hack to apply that rule, but we were aiming at the dark corner here. So now we'll go over to the secondary image. We'll reflect to the secondary image on the other side. Line up where it struck the mirror.
Love it. Love it.
At that corner. And we will bounce to the other side. Then we started looking at 3. Then we were looking at 2.
Oh, this is so cool.
Careful not to draw dotted lines anymore. You can't look at more than 1 image truly at a time.
Oh, I love that too.
So we bounced to
This is
2.
really cool.
Now we're going to go over here and we're going to bounce to 1.
Oh, he's going to 3.
We're again lining up with the corner.
I don't know if he meant to do that.
Oops. My apologies, folks.
Aha.
So I've not had my morning coffee.
So one of my very favorite things in this whole series is watching when a teacher makes a mistake and trying to figure out, learn from them how to deal with it. And so come on, this is always going to happen. It's always, always, always going to happen as a teacher. And so you have to understand how to deal with it. So it just happened. And you saw the look on my face. I was like, oh, I don't think he meant to do that. And so then I was like all ears trying to figure out how does he deal with it. So let's just go back 5 seconds, maybe 5 more. And let's really listen to how he deals with it.
Whoops. My apologies, folks. Until I've not had my morning coffee yet, and I don't want to remake this video. The trick to this is that you're counting down. We start by aiming at the tertiary image.
Love it.
Then we bounce to a secondary image. Next, we bounce to a primary image.
Love it.
A trick to help you is that if you were looking at the darkest corner of our image the first time, every bounce should be aligning with the dark corner.
Man, this is so
You have
cool.
a domino like
And that's just going to go
One
bounce
of the ways
right
I
up.
knew I
again.
had made a mistake is
All right, I'm going to stop. This has gone a little bit long, but wow, just that last part was worth it. So I love this. The angles are changing. Is that right? Nope, these angles wouldn't be changing. And so you could do this with a protractor. And so, but instead, he's really using these targets as ways of, man, this is so cool. And so what's really happening is light's going ding, there's this last little piece he has to draw. It's going ding, ding, ding to your eye, but your brain is just so used to triangulating that it has it coming back from over here. He could do the same thing with this corner or this here. You would see these things converging to the eye. Man, this is so cool. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.